In this video, we're going to introduce the linear congruential generator, which is one of the most popular methods of generating uniformly distributed pseudo-random variates. So in this MATLAB window, I've created a new script. So I'll call this LCG test or something like that. And I'm going to enter the formula for the linear congruential generator. And it's a very simple formula. I need three constants predefined. So I'll define a value a, which I'll define in a moment, a value c, and a value m. And the formula is as follows. Remember that the linear congruential generator, or any pseudo-random variable, is one of a sequence of variables in which each member is uniquely defined by the previous member. So in the case of the LCG, the formula for generating successive values is I take any value x, 0, say, and to obtain the next value in the sequence, I multiply x0 by a, I add c to it, and I take the modulus of all of that. And the modulus I take with the constant m. So what does that mean? Well, let's oh, I should make that equal x1 equals that. So let's generate a set of variates and look at what they look like. So I'm going to, in this particular test, of course in a real LCG, that you would find, like the rand function or a simpler version of the rand function, because the rand function in MATLAB is not a LCG directly. You would ask for a single value, and those single values would be given to you from a list. So somewhere inside that function must be a memory of the previous value that it gave you. But here we're just going to generate them successively. So I say for I equals 1 to n and end. And I'm going to generate my samples. I'm going to obviously call them xi. And I'm going to generate each value based on the previous value. And of course I need the initial value, so actually I can't run from I equals 1, I have to run from I equals 2. And I'm going to define x1. I'm just going to give that some number. I'm going to give that the number 3. So x1 is actually the seed. It's the initial value in the sequence of numbers. So if I start with a different seed value, the sequence of numbers I will generate will be different. Now let's look at a simple version of the LCG. In fact, what I'll do first, I'll just save it. I'll call it LCG test. And I'm going to make m equals 12, which is a very low number. I'm going to make c equals 5 and a equals 1 for reasons that will become apparent later. So I'm going to generate 1,000 samples. And I'm just going to histogram the values x to see what they look like. And I guess at the top I should close all and clear all, as we often do in MATLAB. So I'm going to save that. I'm going to run it, see what happens. So it generated 1,000 values and it doesn't look too bad. You can see that I'm generating numbers which are 1, 2, 3, 4 and so on. I can just check to see what those are by asking for what the values of x are. So you can see that I have 1,000 values of x, and these are my 1,000 random numbers, and all of them lie between 0 and 11. Now why is that? Well, you can see in the definition of that sequence that I'm adding some constant to x and I'm multiplying that value of x, that's the value, that's any one of the numbers in the sequence, so it might be 9 for example. I'm multiplying that 9 by a, which in this case is 1, so it's just 9 again, and then I'm adding 5. So 9 plus 5 equals 14. And when I take the modulus of that with 12, then the result is then 2. So the next number in the sequence is 2. So because this calculation here is an integer, all the numbers that come out at the end are also integers. And they're integers from 0 to 11. In other words, they're effectively the hands on a clock. So if I ask for a larger number of samples, and let's change the initial value to show that it has no effect as well, we'll run it one more time. Now you can see that I'm actually getting too many numbers at 0 and 11. I think this could be a an artifact of how I've done the binning. So let's ask for the binning to be done. I'll ask for 12 bins just to see if that will get rid of that problem. Yes, it does. Okay, so you can see that the numbers which have been generated from 0 to 11, they've been binned in 12 equally spaced bins, and the bin centers, as you can see, are 1, 2, 3, 4, and so on. I think if we expand that, it should be a little bit more obvious. It's 1, 2, 3, 4, and so on. And they are uniformly distributed, as we can see. So this is the linear congruential generator, which gives us numbers on a clock. Now, to generate numbers between 0 and 1, all I have to do is divide all the values x by the value m. So x equals x divided by m now gives us a set. In fact, I probably should put a dot there just to be on the safe side. This should now give us a set of numbers between 0 and 1 instead of between 0 and m. So if I run that again, I'll just save it and run it. And here we are. We have a pseudo-random set of numbers. Now, as you can see, because m is small, then the numbers can only be returned as 1/12, 2/12, 3/12, and so on. So clearly in a real random number generator, this number has to be much larger. So let's enter in some values which are quite common. I wish to have a fairly precise value. You know, the numbers can lie anywhere between 0 and 1 with a fairly fine gradation between them. So I'm going to enter 2 to the 31 in m. Now clearly a and c now have to be fairly large numbers. Let's just find, let's enter c as 0 this time, just to show that that sort of thing is possible. And we'll enter in some value which happens to be quite commonly used, which is 7 to the power 5. If you're interested, what is 7 to the power 5? It's just a fairly large number, 16807. So you'll see that when a is chosen as this number, we're multiplying the previous value by 16807. So if the value was, say, 124657, right, times 16807, that number is 10 to the 9. So if this happened to be the first number in the sequence, you can see that simply by multiplying the previous value successively by 16807 means that these numbers will actually go up in steps of about 10 to the 9. So I will get quite a few of them until this modulus function, until this value m, which serves as the boundary to the modulus function, it'll take some time before that starts to act. So I have to generate a fair set of numbers if I use 1, 2, 4, 6, 5, 7 as my initial seed before I get a sequence of numbers which actually goes down as well as up. Nevertheless, let's try it out. So I'm going to leave the same seed value here, a very small number. I'm going to generate 5,000 numbers as before, and let's see what it looks like. So I'm going to do a histogram with 10 bins. In this case, because I'm generating numbers from 0 to 1, I'm just grouping them into 10 bins to see what they look like. And I do the same loop as before, except now, of course, m is much larger. So let's run that. And there we are. So you can see that the histogram that's been generated does seem to have the right kind of features. And as we saw in a previous video, you can test this random number generator to see if the fluctuations of the numbers around the expectation value, which in this case is 500 in each of the 10 bins, you can see if that fluctuation is as you would expect. So you can see it's possible. This is one of the tests that we can use to see if our random number generator does actually possess the statistical qualities of a pseudo-random generator. Okay, the numbers really are pseudo-random. There are a large number of these tests, and this is a very subtle area that we need to take care of. But the simplest of these tests is to look at whether or not the numbers are actually uniform, which they appear to be. We would have to take the means of each of these values to see if they're all the same, and look at the standard deviations to see if they behave themselves in the right way. In other words, that the standard deviation goes as roughly the square root of the number in each bin, although as we saw before, that's not quite correct. But nevertheless, we can apply these tests and we can obtain pseudo-random variates. So just to recap, this initial value here, this is the seed for the random number generator. M is a number large enough that we get a fine enough gradation between the random numbers that we generate. And these two values here, A and C, there has to be some kind of rule that relates them, as you might imagine, if you think about the relationship between A and C. So I get all the numbers in the clock numbers we saw before. If we wish to generate all of them, not miss out any, I need to choose appropriate values of A and C. Otherwise, I may only get the numbers 2, 4, 6, 8, 10, and 0, for example. So I need to choose these numbers appropriately. Now, there are many possible choices of these numbers, and different random number generators use different combinations, but most of them use M values which are fairly high. Okay, so that's it. In another video, we'll look in a bit more detail about the perils of using these pseudo-random number generators.